There are 7 lexical tokens that are used in the Verilog. They are white spaces, comments, operators, numbers, strings, identifiers, and keywords. Let us see in detail one by one. As very well know that Verilog is a case sensitive language. The keywords, all the keywords that are used in the Verilog, they are represented using only small letters. Here, this is an example. White spaces /b, nothing but blanks. It creates one character spacing. By introducing /t, nothing but tab, one tab space equivalent to 4 blank spaces. And new line /n indicates the new line where the cursor goes to the new fresh line whenever we come across this /n. These three we can call it as the white space characters that are used in the Verilog. When we are going to use the comments, which are not the part but the explanation part of the particular statement, we can use either the single line comment or we can use the multi-line comment. Single line comment, if the comment is of single line, then we can use 2 backslashes. And if the comment is more than one line, so for that we can use the backslash and asterisk. We have to start with this particular backslash and asterisk and end with asterisk and then backslash. Here, these are the few examples which shows how we are going to use the comments in the Verilog programming. So, this was an example showing the module which was written for the D flip-flop with the output as Q and the inputs as DP and clock. So, here the comments saying that the clock, Q and DP are Q is the output and DP and clock are the inputs. These are represented using the 2 backslashes saying that these are the single line comments. And when we are going to see here, if there are multiple lines, instead of using single line comment every time starting with the backslash, 2 backslashes, we can use the 1 backslash and asterisk as seen in this particular example. So starting with a backslash and asterisk mark. So we are specifying the outputs and inputs and then end with the asterisk and then backslash. So in this way, we can use the comments in the Verilog. Coming to identifiers, these identifiers are the names that are given to the variables, the module signals that are used in the module, the parameters, the functions that we are going to use, and different tasks that we are going to use. We can identify all this or represent all this using the keyword called as an identifier. So all the characters of the alphabet or an underscore can be used as the first characters for identifiers. How to represent the numbers in Verilog? We can represent the integer numbers, the real numbers. So integer numbers, both the positive and negative numbers. Generally, the numbers, the size of the length of the particular representation, it takes 32, it is of 32-bit wide. Each number is represented in Verilog as 32-bit wide. If the length is very small, means 4 bits. If it is occupying 4 bits, then rest of the bits you have to append 0 onto the left hand side to make it as 32-bit. The real numbers, either we can use the decimal numbers or we can also use the scientific notations. So 4.3 indicates the decimal number and 4.3 to the power of 2. E2 means 4.3 whole square to the power of 2. Like that we can represent the scientific notation in the Verilog. Coming to how to represent the strings means those strings can be identified by using two double quotes. Starts with the two double quotes and then end with the double quotes. So this is a string. Is written. The statement is this is a string. So we are representing that particular thing within the double quotes, indicating that it's the string. Coming to the logical values, any digital logic, it will have only two values. Digit means two. So logic 1 and logic 0. And when we are going to deal with the Verilog, along with 0 and 1, we are going to have two different logics, two more different logics called as X and don't care. Sorry, X and Z. X stands for the don't care, as already know in the digital logic, and Z stands for the high impedance state. If any of the output is not connected to the next circuitry or left alone or floating output, we can call it as that. Then we can say that that particular output is in high impedance state. Coming to the data types, there are two types of data types in Verilog. Net data type and then Verilog data type. Net data type and variable data type. Net is nothing but a physical connectivity between one block to the other block, which is used to transmit a signal from one gate to the other gate. We can call that connectivity, the physical connectivity, we can call it as the net data type. Example of net data types are wire, trior, tri-zero, supply 1, tri-word, WANT, triant, tri-1, tri-register, supply 0, supply 1. All these are the net data types. As already said, wire is nothing but it comes under the net data type, which represent a simple wire doing an interconnection. So if we are declaring the output as a wire, the output will take only a single value, whether it may be 0 or 1, like that. So if you are going to talk about try, along with the 0 and 1, the output can take more than one value, more than one value of the signal. That means it may take logic 0, logic 1, or it may be driven into high impedance state, Z. Three states, logic 0, logic 1, and high impedance state. So that's why we can call it as try. The output may take the value as 0, 1, or Z. Variable data type, it's nothing but a storage. It represents the storage device or storage element. Register, REG stands for register, time, integer, real time. These are the few examples that we can give for a variable data type. Here, one of the example is given as reach 15 down to 0, memory 511 down to 0. This is nothing but memory. It's an array of about 512 locations, starting from 511 to 0, nothing but 512 locations, and each location is of 16-bit data. Each location, among 512 locations, each location occupies 6-bit data that can be represented in this manner. As we are writing the program in gate level, when we are going to write a program in gate level, we have to instantiate the gates by its name. Here, for an AND gate, the AND primitive, the mode of instantiation, how can we instantiate means A and D, small letters with the small letters A and D stands for an AND instantiation. Already it is predefined in the programming language. And whenever we are writing the program at gate level, we can instantiate the AND gate as A and D with small letters. You can give any name to the particular gate. If more than one AND gates are there, you can give the names as G1, G2 and so. And this AND gate has one output called as O and 8 inputs. This indicates that it is an 8 input AND gate. Similarly, you can instantiate the OR gate by its name OR, small letters, NAND gate, NOR instantiation, XOR, XNOR, buffer gate, and NOT gate. Buffer gate, nothing but whatever may be the input that we are going to give, the same output we are going to get. Now coming to the test bench, this is one example of a module that describes the test bench of an AND gate. Module name is test underscore A and D. We can give any name to the module name. But the keyword is keyword. We have to start with module. Module name. Module name is user defined. Module is keyword. Inputs are represented as registers. So REG. A1 and A2 are the registers of two input AND gate. While is nothing but output. Output is declared as while in the test bench. So B is the output. And the set of inputs are given using the initial block. So initial. As there are more number of statements, we have to start with begin and then end with end. So at 0 nanoseconds, A1 and A2 both are going to take the value as logic 0. At 3 nanoseconds, hash 3 indicates at 3 nanoseconds, A1 becomes equals to 1. A1 is changing from 0 to 1. At 3 plus 1, all the statements within the initial block are always block. These are belonging to the behavioral modeling. Statements. All the statements within this block run sequentially, that is one after the other. So thereby the next statement is hash 1, A1 equals to 0 means the instances, time instances gets added here one after the other means after 3 plus 1, the instant becomes 4. At 4 nanoseconds, A1 equals to 0. At 6 nanoseconds, A2 equals to 1. At 10 nanoseconds, A1 equals to 1. At 30 nanoseconds, A2 equals to 0. At 40 nanoseconds, A2 equals to 1. So these are the timing instances that we are going to that are given in the test bench. We can use any other timing instances also. So we are ending this particular initial block with the end statement. Here we are instantiating for what we have written this test bench is to test a 2-input AND gate. So here we are instantiating the main design module program that was written for the AND gate by its name A and D. At present, the name for that particular AND gate in the test bench, it is given as G1. Outputs within the parenthesis, output followed by inputs. So here output is B and A1 and A2 are the inputs. The same order that we are given in the design module, we have to follow the same order in the test bench also. Then using two initial blocks, one for displaying the results, either we can use the $display statement or we can use the $monitor statement. Here we are going to use the $monitor statement where we are displaying the time. So by using $time, in this particular, when we are going to use $time, time is specified. And within the double quotes, we are representing the value of A1 in terms of A1 is displayed in terms of binary. A2 is also displayed in terms of binary. The output B is also displayed in the form of binary. Percentage B stands for the binary. And here, after the double quotes, these things indicates in what order they must be displayed. So, first A1 will be displayed, then A2 and then B. This particular program simulation is going to be stopped at 100 nanoseconds. So that's why it is written as initial hash 100. You are going to use dollar finish. You can use either dollar stop or dollar finish. Dollar stop just indicates the suspension, the execution is going to be suspended for certain amount of time. But when we are going to use the dollar finish, you are coming out of the program, out of the execution program. So starting with the module, you have to end the particular module. So this is the simple program, a test bench program that is written for an AND gate. How we are going to give the set of inputs, either you can use the initial block and always block. The difference between initial and always is whatever may be the statements within the initial block, they are going to be executed for only one time. But when we are going to use the always block, until the condition is satisfied, all the statements are executed continuously. So this is the difference between initial and always block. Coming to difference between dollar monitor and dollar display. Dollar monitor means every time whenever the variables are going to be changed, input values are going to be changed, all the values are going to be displayed if we are going to use the dollar monitor. If you are going to use the dollar display, only that particular instant will be displayed. And these are the results that we are going to get. As we have specified, dollar time, first A1 will be displayed, then A2 will be displayed, and then B will be displayed. So this is the dollar time. Because of using dollar time, we can observe the timing instances, and we can have, because of using dollar monitor, we are going to have all the whenever A1, A2, whenever there is a change in A1, A2 values, we are going to have the corresponding outputs that are being displayed.